It does not enter into the subsequent reasoning. We now have to define the operation x plus a, which consists in adding the number a to any given number x. Suppose that we have defined the operation x plus a minus 1. The operation x plus a will be defined by the equality x plus a equals to x plus a minus 1 plus 1. We shall know what x plus a is when we know what x plus a minus 1 is. And as I have assumed that to start with we know what x plus 1 is, we can define successfully and by recurrence the operations x plus 2, x plus 3, etc. This definition deserves a moment's attention. It is of a particular nature which distinguishes it even at this stage from the purely logical definition. The equality 1, in fact, contains an infinite number of distinct definitions, each having only one meaning when we know the meaning of its predecessor. Properties of addition. Associative. I say that a plus b plus c equals to a plus b plus c. In fact, the theorem is true for c equals to 1. It may then be written a plus b plus 1 equals to a plus b plus 1, which, remembering the difference of notation, is nothing but the equality 1 by which I have just defined addition. Assume the theorem true for c equals to y. I say that it will be true for c equals to y plus 1. Let a plus b plus equals to a plus b plus. It follows that a plus b plus 1 equals to a plus b plus 1, or by definition 1, a plus b plus 1 equals to a plus b plus 1 equals to a plus b plus 1 equals to a plus b plus 1, which shows by a series of purely analytical deductions that the theorem is true for plus 1. Being true for c equals to 1, we see that it is successfully true for s, c equals to 2, c equals to 3, etc. Commutative. 1. Let us say that a plus 1 equals to 1 plus a. The theorem is evidently true for a equals to 1. We can verify by purely analytical reasoning that if it is true for a equals to y, it will be true for a equals to y plus 1. Now it is true for a equals to 1, and therefore is true for a equals to 2, a equals to 3, and so on. This is what is meant by saying that the proof is demonstrated by recurrence. I say that a plus b equals to b plus a. The theorem has just been shown to hold good for b equals to 1, and it may be verified analytically that if it is true for b equals to beta, it will be true for b equals to beta plus 1. The proposition is thus established by recurrence. Definition of multiplication. We shall define multiplication by the equalities 1. A cross 1 equals to a, 2. A cross b equals to a cross b minus 1 plus a. Both of these include an infinite number of definitions. Having defined a cross 1, it enables us to define in succession a cross 2, a cross 3, and so on. Properties of multiplication. Distributive. I say that a plus b cross c equals to a cross c plus b cross c. We can verify analytically that the theorem is true for c equals to 1. Then, if it is true for c equals to y, it will be true for c equals to y plus 1. The proposition is then proved by recurrence. Commutative. 1. I say that a cross 1 equals to 1 cross a. The theorem is obvious for a equals to 1. We can verify analytically that if it is true for a equals to y, it will be true for a equals to y plus 1. I say that A cross B equals to B cross A. The theorem has just been proved for B equals to 1. We can verify analytically that if it is true for B equals to Y, it will be true for B equals to Y plus 1. 4. This monotonous series of reasonings may now be laid aside, but their very monotony brings vividly to light the process which is uniform, and is met again at every step. The process is proved by recurrence. We first show that a theorem is true for n equals to 1. We then show that if it is true for n minus 1, it is true for it, and we conclude that it is true for all integers. We have now seen how it may be used for the proof of the rules of addition and multiplication, that is to say, for the rules of algebraical calculus. This calculus is an instrument of transformation which lends itself to many different combinations than the simple syllogism, but it is still a purely analytical instrument and is incapable of teaching us anything new. If mathematics had no other instrument, it would immediately be arrested in its development, but it has recourse anew to the same process, that is, to reasoning by recurrence, and it can continue its forward march. Then, if we look carefully, we find this mode of reasoning at every step, either under the simple form which we have just given to it, or under a more or less modified form. It is therefore mathematical reasoning par excellence, and we must examine it closer. 5. The essential characteristic of reasoning by recurrence is that it contains, condensed so to speak, in a single formula, an infinite number of syllogisms. We shall see this more clearly if we enunciate the syllogisms one after another. They follow one another, if one may use the expression, in a cascade. The following are the hypothetical syllogisms. The theorem is true for the number 1. Now, if it is true for 1, it is true for 2. Therefore, it is true of 2. Now, if it is true of 2, it is true of 3. Hence, it is true of 3, and so on. We see that the conclusion of each syllogism serves as the minor of its successor. Further, the majors of all our syllogisms may be reduced to a single form. If the theorem is true for n minus 1, it is true for n. We see, then, that in reasoning by recurrence we confine ourselves to the enunciation of the minor of the first syllogism, and the general formula which contains as particular cases all the majors. This unending series of syllogisms is thus reduced to a phrase of a few lines. It is now easy to understand why every particular consequence of a theorem may, as I have explained above, be verified by purely analytical process. If, instead of proving that our theorem is true for all numbers, we only wish to show that it is true for the number 6, for instance, it will be enough to establish the first 5 syllogisms in our cascade. We shall require 9 if we wish to prove it for the number 10. For a greater number, we shall require more still, but however great the number may be, we shall always reach it, and the analytical verification will always be possible. But however far we went, we should never reach the general theorem applicable to all numbers, which alone is the object of science. To reach it, we should require an infinite number of syllogisms, and we should have to cross an abyss, which the patience of the analyst, restricted to the resources of formal logic, will never succeed in crossing. I asked at the outset why we cannot conceive of a mind powerful enough to see at a glance the whole body of mathematical truth. The answer is now easy. A chess player can combine 4 or 5 moves ahead, but however extraordinary a player may be, he cannot prepare for more than a finite number of moves. If he applies his faculties to arithmetic,